Okay, so can somebody sort of give me the definition of a power law? It's a mathematical definition and maybe an intuitive definition of what it means. So the answer is yes, somebody can. The question is who? Okay. Someone over here. Okay, yeah.
I could try. They describe empirical scaling relationships. I guess that's not really a definition, it's like a fact about power laws. But
Yeah, so they do describe scaling relationships. What's special about the way they scale? So first of all, what do you mean by scaling relationships?
like the scale at which something is. It sounds like we looked the other day at the stock market fluctuations for like over a period of a month versus a week versus like a year, and those are different scales.
Right, yeah, so there's something special about, I mean, we could imagine looking at any function over different scales, right? There's something in particular about a power law that's special, yeah.
So does it just say that the log of the log of the frequency of an occurrence of certain value decreases linearly with that certain value, with the log of those values?
Yeah, so you're saying that you could write it down like this, like you have some log of some value y, and that goes linearly, so it goes like this, log x, maybe there's some slope of that line, and maybe there's some constant, I'm gonna call log b, okay? So yeah, if we plot it, basically if we plot the function y as a function of x on a log plot, we'll get a line. So that's one way to think of it. What does this mean for how y is related to x? What form?
It's an exponential function of x.
Yeah, it's an exponential function, right? So I can write some sort of, it's called alpha, just some constant up here. So these two things are identical. In fact, if I exponentiate both sides of this equation, I get, well, what do I get? Take the exponential of each of this equation. Yeah, so actually in this case it'll be an m, and then there's a b. So this really is the definition of a power law. I would say this, I mean they're all sort of definitions, but this is the primary definition. That's just something that varies as the independent variable to some exponent, maybe times some constant. Yeah.
In every example that we saw, is the exponent negative? That was the question I got.
Yes, that's a good question. So in general, power laws don't have to have negative exponents. In fact, in the other paper, the fractal nature of nature, there's ones that don't have negative exponents. But you're right, everything in this paper had negative exponents. So why is that? That's a very good reason for why that is.
Bigger things are infrequent.
Well, what were we looking at? So we weren't just looking at y, we were looking at special function. What function was that?
Well, probability distributions.
Yeah, probability distributions. So
Sum to one.
we're looking at things like this, exactly. So you know, if I write down this is a probability, I have to be able to normalize this thing. So it has to be the case that the integral of px dx equals 1 over all values of x. So whatever the probability is that I get a value x, I have to get some value of x if I choose to move that x. And if this m were positive and we try to integrate that, we'd get infinity. We'd get something equal to that. So in order to have a real probability distribution that describes frequencies, this has to be negative.
Just weakly negative?
Okay, that's another good point. So how negative does it have to be? Can you tell me that? So let's say I write it as p of x goes like x to the minus alpha, and so I'll ask you guys, can alpha equal 1/2? Will that work?
I mean, in general, they want alpha to be bigger than 1 or bigger than 2.
Yeah, bigger. There's something about being bigger than 1 that they talked about in this article. So it turns out, and it's pretty easy to show, I'm not going to go through it, but if you integrate this, and you want this thing to basically be less than infinity, you want this to give you an actual answer, then this alpha has to be bigger than 1. If alpha is less than 1, like for example, let's say alpha is equal to 1, we'll get a natural log of x, and we'll try to evaluate that from infinity to minus infinity, and natural log of infinity is infinity, so it's not really well defined. So, in all the things we're going to be talking about today, let me write this down here. Charge over here. So this is, we're going to be talking about things like this. P of x goes like x to the minus alpha, where alpha is greater than 1. And in particular, this article typically deals with alphas less than 2. But there's not a great reason it has to be less than 2. Just typically that's what we find in nature. Okay, so that's the definition of a power law that we're going to be using. And what about the sort of intuition behind power law? What's so different about this distribution than, let's say, Gaussian or normal distribution? Or any other sort of distribution you guys are used to using?
Fat tail?
A fat tail. What does that mean? So if I draw a picture of it, typically we draw these things, they might look like something like this. So this is what we mean by fat tail. The thing doesn't decay very quickly. Is there a sort of mathematical meaning to fat tail? Like how fat is fat?
Fatter than an exponential function?
Yeah. So does everybody get that from the article? So if this thing decays faster than exponentially, it doesn't have a fat tail. So an example of that is something like e to the minus x squared. This is a Gaussian distribution. And e to the minus x squared decays faster than e to the minus x. But anything like this decays slower than e to the minus x. So that's the boundary between a sort of fat tail and a thin tail. It's the exponential function. Okay, so the tail grows faster than exponentially, or decays slower than exponentially. What else? What about just the, some more, less mathematical definitions and more intuitive? What if I have a distribution of rock sizes, and one of them is Gaussian distributed, the other one is power law distributed? What's going to look different about those two?
In the power law case, we will be surprised at how high the probability is for extreme events, so like huge rocks or really tiny rocks. Whereas in the Gaussian distribution, we would expect the rocks to kind of tend towards the mean or not differ that much from the mean.
Yeah. So for a power law distribution, we have a huge range of scales. The scales vary by orders of magnitude. So shoe size is something that is Gaussian distributed. All the guys in this room probably, if you plot their shoe size, it's centered around a mean for the Gaussian, same for all the girls, and same if you put everything together. So no matter which way you do it, you get some sort of average shoe size. Like we know that our feet on average are about the size of 1 foot, right? 1 foot. That's why we have that name. Two factors of 2 or 3 or something, not factors of 10. We don't have people with 10-foot long feet and 100-foot long feet and 1,000-foot long feet and a centimeter long foot. It's kind of a confusing thing to say. But if we did, that would be like power law. So power law distributions have things over all scales. And certainly feet and shoes and test scores and sizes of trees and buildings and things like that are not distributed that way. So I want to show you guys a...
Gaussian will have an infinite, almost zero probability of an incredibly large thing on the tail. So you can't just say that Gaussian differs because there's no possibility of a very large thing.
So
It's just
because the
not that
Gaussian
probable.
decays slower than exponentially, you can show that there's basically zero chance you're going to get something that's out here in the tail. mathematically there's a difference. There's the Gaussian, so the way they, I think a good thing they do in the section on mathematics of, where they talk about where is it? The mathematics of power law, section 3, they talk about the moments and they talk about the largest value. And that's really where you get the distinction. So if you take well, can somebody tell me what the difference is? So he says that even Gaussians have a small probability that you're going to get something really, really big. Based on the moments of the distribution, so like the mean or the standard deviation, or the largest value, if you take a set of samples from distribution and you pick the one that has the largest value, what's going to be characteristically different about the power law distribution and the Gaussian distribution?
Orders of magnitude.
So what do you mean by that?
Like if you take a set from a power law distribution, the difference between the top and the bottom are going to be orders of magnitude different. And you might have maybe 1 or 2 orders of magnitude in the Gaussian distribution, but not like. So I don't know, that's a fuzzy definition. But
Yeah.
That would be my intuition.
That gets it intuitively right. So mathematically, what they say in section C here is if you take some finite sample of points from a Gaussian distribution, you can. Okay, so we'll play a game like this. You have a big box. It has a bunch of things in it, and this one has a Gaussian distribution. And then we have one over here that's power law. So what we're going to do, these boxes have an infinite number of data points in them. We're going to pull out, let's say we first pull out 5 points from the Gaussian, 5 points from the power law. Pull out 5 points in each one. And we find we do 2 things. We find the average of each of these sets of 5 points, and we find the maximum value. So I'm going to write this as x. This is what we typically use for average. So x5 means we're taking the average of 5 points. And then I'm also going to have some sort of a max value. So then the next thing we're going to do is we're going to keep playing this game. We're going to draw up 10 sample points. We're going to draw 100, 1,000. And I'm going to ask what happens sort of in the limit as I take infinite number of sample points. So in the Gaussian case, both the average and the maximum will quickly converge to some value. So I can, if I pull out, let's say 100 points, and I calculate the mean of that, and I calculate the max value of that, and I do the same thing for 1,000,000 points, I'm going to get about the same answer. For the power law distribution, something fundamentally different happens. So what is that?
I guess the more samples you take, the higher the mean
Yeah.
you will tend to get.
So as you increase your number of samples, your mean diverges. It goes to infinity. So there's
If the alpha's not too big.
if the alpha is not too big. So there are power law distributions where you will get a finite mean, but you won't get a finite standard deviation. And it's true that for a Gaussian distribution or any sort of normal distribution like this, every single moment, so you're, to remind everybody what I mean by moments. I mean this thing. So I'm going to integrate the probability distribution multiplied by x to the nth power, and that's going to be the nth moment. So this is a fancy word for things that we're very used to. Averages, standard deviations, all of these things are related to powers of these. So the average is just m to the first power. The standard deviation is related to m equals 2. And there's other names like kurtosis and skewness and all these weird things that go with the higher moments. So for a Gaussian distribution, all of the moments are going to be finite, and they're all going to be well defined. For the power law, the bigger I make the sample, the bigger the moments are going to get. Until if I make the sample infinite, I get infinite mean, and also the maximum will do the same thing. So if I keep increasing the size of the sample, the maximum will keep increasing without bound. Yeah.
I guess one way to describe the difference is that with a Gaussian, you have a well-defined measure of a central tendency. You have a mode, you have a mean. Those really exist. That's really the main thing you want to get out of a Gaussian distribution, is to find out what the mean is. But in the power law, there's no central tendency. It's just
Yes.
spread out.
Yeah, so
There's no typicalness.
there's no typicalness, exactly. So for Gaussian, there is some really rare events that could happen, but there's a very well-defined typical value. For a power law, that's not true. If I pull out of a power law, I am fairly likely to get any sort of value. Yeah.
But when you're actually dealing with power laws in real life, you don't have infinite samples,
Right.
and so you have an average.
You have an average, but that's a good point. So you have an average. In this case, even if I make the number of samples 1 billion, I have an average and I have a maximum.
But also, I thought a lot of those natural ones have a pretty low alpha.
So you mean the mean wouldn't be characterized? But even
Oh, yeah, sorry, other way around, yeah.
but
For
if
high alpha, the mean is well characterized.
right,
Yeah, for low alpha, you'd expect it not to be.
yeah. But even if the mean's not characterized, if you take a finite sample, you get a finite mean. There's a finite number of numbers here. They have finite values. You average them together, you get a finite number. So, can someone tell me why, even though we get a mean, it's not a really useful thing to worry about? Yeah.
Because as you change the sample size, the mean changes,
Yeah.
so it stops being a useful measure.
Yeah. So it's in fact, it's never a useful measure because it's always changing. It's a number. It exists. We can calculate it, but it doesn't tell us any information about the distribution because it's always going to keep changing. So there's no point in calculating the mean or the standard deviation of these types of distributions because they don't tell you anything about the typical value. In fact, there is no typical value. That's the important part.
It's kind of like if I showed you a person, you could say, is this person the typical height? If I showed you a rock, you'd say, is this a typical rock? Well, a rock can be that big or it could be
Yeah,
60 meters big.
exactly. That's a great segue. I want to show you guys some pictures of rocks that are different distributions. Okay, they're not really rocks, they're just dots, but close enough. So where is the picture?
I see what page on it.
Okay, so all of this is, I'm talking about math and well-definedness and typicalness and all these sort of weird things. Why don't we just look at two distributions of rocks, let's say, and see if we can tell the difference. Can you make Okay, so here's a distribution of dots. I'll show you two different distributions. Now I want you guys to tell me which one is sort of the normal distribution and which one is the power law. So here's the first one. Here's the second one.
You can tell from the title.
Yeah.
Unless you mix them up.
I did. So there's basically the difference. I mean, in this case, there's sort of a typical size. Yeah, there's some that are a little bit smaller, and yeah, there's some that are a little bit bigger. But the smallest thing you find is likely to be something about this size, and the biggest thing you find is likely to be something about this size. And the power law, which you see that there's all different sizes here. There's really, really massive ones, and occasionally we would find one that takes up the whole screen. And there's also really tiny ones that we can't even see on this, the zoom one. And I can't do this here, but if I were to zoom into this picture, it would always look the same. There would always be really big ones.
if we zoom in here.
Can you do that?
If we zoom in here, you see that the average increases.
Yeah, so this is the Gaussian again. If you zoom in, you can see that the biggest dot gets bigger.
And if we go into here and we zoom in, it still seems.
Let's go.
Looks the same. So if you think about traveling around, and I like this term, but it's kind of weird, traveling around in zoom space, where I'm able to like zoom in and zoom out. If I zoom in and zoom out in the power law, I can't tell where I am. I can't tell what scale I'm at. It's like that picture that Oana showed you of the rocks and the camera lens, and we all thought they're small rocks, but in fact they were big rocks. Whereas for the Gaussian, if you sort of zoom out and zoom in a little bit, you can tell what scale you're at. There's a characteristic scale. For power law, it's not a characteristic scale. Okay. So is the internet working now?
No.
One thing I wanted to show you guys, so although the math might seem complicated, you all are pretty good at recognizing power laws versus more standard distributions. Both visually, like that, it's pretty obvious which one's which, and with your ears. So you can go online at home and you can listen to different noise spectrums. So there's so many types of noise. There's white noise, which we call pink noise, brown noise. Okay. So these are all the frequency distribution of the sound. In all three cases, is power law distributed. This is distributed like 1 over f to the 0. It's just constant. White noise means all frequencies are equally represented. Pink noise is sometimes called 1 over f noise. So low frequencies are very common, and low frequency and high frequencies are very rare. And then brown noise is 1 over f squared. So if you there's a Wikipedia article about this stuff. If you go in and you listen to each of these, you can clearly tell the difference between this one, this one, and this one. So not only can we, and if I played you something like Gaussian noise, which is just centered around a single frequency, it would be incredibly obvious which one's which. One would sound like noise, like shh, that kind of thing. And the other one would sound like a tone. So not only can we distinguish between power laws and normal distributions, but we can distinguish between different types of power laws, different exponents of power laws, pretty easily with our ears. But unfortunately, in science, it's not typically what we're confronted with sounds or pictures. We typically look at functions. So let's go back and talk about what this thing looks like if you were just to plot the distribution. If you were to plot that thing. So can somebody tell me, so we talked about how if you plot this thing on a log plot, you get a line. Let's go through that one more time. If we have something like p goes like x to the alpha, then I can take the log of p, and that's going to go like the log of x to the alpha. And does somebody remember what this thing is? Like, what can I do with this alpha up here? Alpha log n. Yeah, you can bring it out to the front, so you get this. So power laws, if you plot them on a log plot, are going to be straight lines. And the slope's going to be alpha. Okay, so here's a question for you guys. If I want to find out if I have a power law, clearly it's better to plot it on a log plot than on a plot like this, a linear plot, because I can't really tell if this is growing faster or slower than exponential, but I can certainly tell this is a line. In real data, we're going to have some sort of noise. So we might get a bunch of points, and it might look like this. It's not going to be a perfectly straight line. And we're also not going to have points over the whole range of x. We're going to have some sort of cutoff based on how much data we can actually get. So my question is it enough just to sort of plot it on a log plot and see that it looks sort of like a line? Is that enough to say this is a power law?
No.
No. Why not?
there's other stuff that can look like that.
Yeah, there's other stuff that can look like that. So maybe what our real function does is it, instead of being a line, it sort of starts off as a line, curves down at the end. And typically in these plots, you have a lot more noise out here. So this is what our data looks like. It would be hard to tell if, it would be almost impossible to tell if it was this or this. So that's the important thing to remember. In practice, if you go to a physics conference, it's a really good example because physicists tend to love power laws. But if you go to any sort of scientific conference, you tend to see a lot of power laws. People think they're interesting. But not everybody does a very good job at distinguishing between power laws and power law-like things. In fact, the pictures that Newman puts here, he puts a whole bunch of plots of different power laws. And he says that most of these are probably power laws because he was pretty rigorous in making sure that these were power laws, but you can't be sure. You don't have enough data, and there's a lot of noise in some of these. So these could also be power law-like things.
Why does the noise generally increase towards big log X?
Yeah. Why is it?
Because big values are far less likely. You're far less likely, if you imagine you're sampling through a distribution, you're far less likely to get one of those.
Right. So we know that this is sort of what the frequency looks like. Way out here, we're we have to sample a lot of points to even get one way out here. This is that's a lot less likely. So out here you have a couple points, and over here you have a ton of points, and therefore you have more noise. Generally, if you have more points, you have less noise. So that's the main problem. That sort of near the tail of the distribution, we get a lot of noise. We can't distinguish between power laws and power law-like things, and so the warning is that you need to be careful. If you actually want to use this stuff in research, you don't want to go around saying something's a power law and find out that it's not. Although people do it all the time. Yeah.
What are some things that look power law-like?
Exactly what I was going to talk about next.
Oh.
So there's a couple. There's something called a stretched exponential. There's something called a log normal distribution. The more common one that you see is a log normal distribution. So let me talk about that. Okay, so what a log normal distribution is. You write down the function first. So this looks a lot like a Gaussian, except the only difference is instead of having an x, I have a log x. So this means that if you have a log normal distribution and you plot it on a log plot, so instead of plotting, it should be a p, instead of plotting log of p versus log of x, I'm just going to plot p versus log of x. And if I do that, then I will get a Gaussian with a mean mu and a standard deviation or variance of sigma squared. And you tend to get these things, so we learned a couple weeks ago that the central limit theorem tells us that if you sum together a lot of random variables, you get a Gaussian distribution. If you do the same thing, but now you multiply together a bunch of random variables, you get a log normal distribution. So just like adding together lots of things is pretty common, multiplying together lots of things is common as well. And for that reason, we tend to get log normal distributions. Okay, so now the question is, why would I ever confuse this thing for a power law distribution? So, well, let's do what we did here. We want to plot it on a log-log plot. I'm going to skip a step. So try to work this out on your own. But if you plot on a log-log plot, you get log of p equals log of c you get this. So now if you think about log of p as your sort of y, your dependent variable, and log of x is your independent variable, it's sort of analogous to x. On a normal plot, what kind of function is this? So if I were to plot this on a log-log plot, what would I get?
Okay.
I heard parabola. Any other guesses or answers? Parabola's right. This is a parabola. So this is a parabola that's concave down, it's shifted upwards, and it's shifted over to the right. So it looks something like this. Assume that I can actually draw, and then you got it. Okay, so the question is, how can we ever get confused about this thing being a straight line? Because we just said that we might confuse it, it might do something like this. Why can I confuse that picture for this picture? I'm not here.
If your data points kind of concentrate after the mu,
Yeah, so what if, let's say your mu is equal to 0, or maybe it's equal to some negative number. Then your data points could fall right here. And if you sort of zoom in close enough to a parabola, it looks like a line. In a local region on a parabola, you don't really see the curvature, it just looks like a straight line. So if all my data points were here, I would see something that looks like a straight line in log space, and I'd say, oh, that's a power law. But the telltale sign would be that if I looked far enough out, I would eventually see the thing curve down. Like I see here. So you can imagine this thing being a parabola, a really big one, so it goes out here. Okay? So that's the most common distribution that you'll see that's not a power law, but has a heavy tail, and so you might confuse it for a power law. Any questions about that? I want to go back and ask you guys, so we don't want to confuse the power laws for the log normal distributions, and the problem we have is the noise at the tail. What's a couple of ways that Newman talks about in this paper that we can avoid the noise at the tail issue when we're plotting these?
You had some other technique for calculating the slope that wasn't in the curve.
Yeah, so he has this, let's see, on page 4 at the bottom on the right side, there's an equation 5. That is some way, if you have all the data points, that you can calculate the most likely value for alpha, the slope. And that's using some methods from statistics. But what if I don't want to plot? Is there something else I can plot? Right now I'm plotting this thing, right? I'm plotting P of x, which is the probability distribution. Is there something else I could plot that would be better and avoid this noise problem? So the problem here is the probability distribution. I'm always looking at the probability that the value lies at some x, or right around some x. And so I'm going to get a very few number of points that lie around these big x's, and I'm going to get a really noisy tail. So what's the function I can plot that doesn't have that problem?
CCDF? Is it about that?
A what?
Is it about the cumulative distribution?
Yeah, the cumulative distribution. So why does that avoid the problem?
Because instead of plotting the probability of P, like random variable x equals to a particular x, you plot the probability of it being larger or smaller, I'm not sure, than x.
Yeah,
And
exactly.
because that gives you bigger values, then that kind of erases out some of the noise.
So a cumulative distribution is the probability that instead of it being at the value x, it's bigger than x, bigger than or equal to x.
Usually we mean smaller than x, and
Smaller.
complementary cumulative is larger than x. It's more relation.
I think Newman uses the opposite, right?
Yeah, but traditionally statistics cumulative is smaller, so they call this complementary.
Okay, so
Just like CC.
just to get the notation right, this thing,
That's what the cumulative constant, your cumulative.
yeah, exactly. So this thing is typically, but you could always flip around your direction of your coordinate of your cube. So, this is the typical definition from 0 to x. So this is the small p, this is the probability distribution, and this is the cumulative distribution, and this thing is defined for a single point, and this is the probability that you lie below x. So this would be like big P of x would be the probability that you lie anywhere in this region. That's why we're integrating. It's related to the area under that curve. The thing that Newman actually uses, which I'll call P tilde x, is just 1 minus this, and that's everything bigger than x. So that's just the probability that you lie in this region over here. This avoids the problem because now instead of just trying to find points that are right around here, you get to add up all the points that are here and everywhere behind here or everywhere in front of here. So because you're summing together lots of points, each slice in your log-log plot is a sum over many points, and so you don't have as much noise at the tail. Okay, so I don't want to go through the math on this, but if I have a probability distribution function that looks like this, what is the big P going to look like? And let's say we're using Newman's definition, so I want to look for P tilde. So this, he gives you the answer to this in the mathematics of power law section. I can just write it down. Turns out that this thing will go like, if this thing goes like minus alpha, this will go like x to the 1 minus alpha, and there will be some different constant here. But that's not important. So the important part is the cumulative distribution is a power law if the regular distribution is a power law. So we can calculate this big P, we can plot it on a log-log plot, and we should still get a line. The slope's going to be different, but we can figure out what the original slope would have been. And we don't have the error problem. Okay, so then there's something he calls a rank frequency plot. What is that? Can somebody tell me what a rank frequency plot is?
I thought it was kind of like a histogram, but I could be wrong.
So in the histogram, you have to make bends. You have to say that things are in some range. You have to put them in a bend. For the rank frequency plot, you don't actually make any bends. So he did talk about a histogram, though. That still had the error and the tail issue. So if you look on, so I'll give you a hint. All of these, or most of these things, are not cumulative distributions. They're actually rank frequency plots. That's how he created these. So what a rank frequency plot is, I'll just tell you, is you rank your points. So you have a set of points. So you have a set of frequencies and points. So you say that you sort of draw x with frequency f. That's what that means. And you have a bunch of points x that you get from your data, and you have a bunch of frequencies associated with those. Now what we could do is we can arrange, so the first step is to arrange in order of decreasing frequency. And then we can plot them and we want to plot them in the following way. We want to plot them as the frequency on the y-axis and the rank on the x-axis. So the things with the a rank equal 1 means that it has the biggest frequency. And a high rank will mean it has a really low frequency. So we might get something that looks like this. We plot all of our points. And it turns out that this is exactly the same as the cumulative distribution. And the way to think about that is the number of points that are bigger than, let's say, the rank 1 guy is 0, because he had the biggest frequency. So this is the largest frequency, that means there's no points bigger than this frequency, and that's equal to rank 1. So the rank is actually equal to the sort of number of points that are bigger than that point x. So rank 1, there's no points bigger than it. Rank 100, that means it's 100 points that are bigger than that. So the rank is proportional to this cumulative distribution. Rank is proportional to the probability that the x is bigger than some value x. And so by plotting rank versus frequency, you get the cumulative distribution.
You have to flip rank?
Yeah, there's something we do.
Rank them backwards?
Oh yeah, you're right. I wrote it down wrong. So it's actually rank on this axis and frequency on this axis. And then it's exactly the same as plotting P of x versus x. So the reason I'm telling you this is what you actually do in practice. It's typically, so let's say you have 1 million data points. If you want to calculate the cumulative distribution, you have to first sum together 1 million points, and then sum together 999,000 points or whatever, then you keep going down. So you have to sum every single point together to get a single data point. And it takes a long time. So in practice, this is a lot faster and easier to do, and that's why these plots are almost all rank frequency plots, not cumulative distributions.
So I'm still confused. So in a power law distribution, something that is large will have a low frequency.
In a power law distribution, something that's,
Something
yeah, so something that has a large frequency will have a low probability of occurring, which means it has a low rank. Because we're ordering them in decreasing frequency. So the thing is, so remember this is rank, this is like rank 1, rank 2, rank 3, so on and so forth. Is this confusing to most people? Who's confused by this still? It's fine if you are, it's kind of confusing.
I thought 1 is the most frequent, no?
1 is the most frequent.
Yeah.
Yeah.
That's right.
So it's rank 1, because we're arranging in the order of decreasing frequency. So I'll let you guys, I don't want to dwell too much on this, it's not that important, unless you're actually doing some practice, but just the main thing to take away is that rank frequency plots are the same as cumulative distributions, and so you can use either one.
It's kind of the axes flipped. Maybe that's, its frequency was y-axis.
Is that what's confusing most people? The fact that I have, so the frequency here is the, it's plotted the right way. If you think about it, it is kind of a confusing connection. If you think about this though, you'll, and do an example maybe, you can convince yourself that this is the right thing and you get the same distribution. I don't want to dwell too much on this, it's not that important. If you don't get it, don't worry about it. Just know that it exists. Okay.
Yes.
talked about the moments of power law. So I want to talk about scale invariance now. So often we talked about fractals last time being scale invariant. What did that mean for fractals? Yeah.
They look the same when you zoom in and zoom out.
Yeah, so there's this zoom sort of property. And we saw this again with these pictures of these different sized rocks. When you zoom in or you zoom out, things look the same. So people often say that power laws are scale invariant. Maybe that's the most important characteristic of them. Okay, so I want somebody to tell me intuitively, it doesn't have to be mathematically correct, just why do you think that power laws are scale invariant? Why do people say that? Anybody? Yeah.
There's no distribution around kind of like a central tendency, then I mean, it looks the same. I'm sorry, that's not a very good explanation. But yeah, it's kind of like when we were zooming into the dots of the Gaussian distribution. The bigger dots were still the bigger dots. Things sort of stayed around a central kind of distribution of things.
Yeah.
Whereas when the mean kind of just gets bigger based on your number of samples or smaller. Yeah. I see sort of an intuitive connection there, but I'm not sure I can explain it.
Oh, that was good. So when we zoomed in and zoomed out with something that had a parallel distribution, it certainly looked scale invariant. There wasn't if there was a typical size, so this distribution, the exponential distribution, has a typical size. It's called the decay constant. And if it had a typical size, it's certainly not scale invariant, because if we draw a couple pictures of exponentials, I can zoom out and it might look like this. I could zoom in and it might look like this. So by zooming out and zooming in, I can clearly tell the difference between really far zoomed in, past the decay constant, and really far zoomed out. So you can't do that with power law. Another way to think about it is we know that these things are, so the log space is almost like zoom. It's related to how you zoom in and out. Because here we have things that are really, really small, and things over here are orders of magnitude bigger. So by looking at sort of the function in log space, we can tell something about what happens when we zoom in and zoom out. And we know that we get a line for our power laws. Now, zooming in some sense, means moving this direction. Zooming means moving in sort of this direction. And we can see that no matter where we are in this line, it's always a line. It always looks the same. And so as we zoom in and zoom out, we're always on this line. Every single point line looks the same. There's no scale up there. It's sort of the intuition. I'm going to make that a little bit more formal. So to do that, I want to talk about some properties of log space. So I don't know, how many of you are used to plotting things on log scales like this? Or is this new to some people? Who's used to doing this? Okay. So I want to talk briefly about how to understand some things in log space. So just to remind you of some properties of logs. Log of A times B is log of A plus log of B, and log of A to the C power is C log A. So those are the two main sort of logarithm rules that you learned in high school. And we can use these to understand what happens in log space. So let's say we have some typical function y equals f of x. And I'll just draw it, let's say it looks like this. This is a linear scale. So when I say I want to zoom in, what do I mean? What do I actually do? What I can do if I want to zoom in is I can take x and I can rewrite it in x times some scaling factor, which I'm going to call b. So let's say I take this function and I want to zoom in by a factor of 2. So I sort of want to zoom into here, then expand it back to this size. I can make b equals 1/2. So if I make b equal 1/2, then everywhere x used to equal 1. So let's say this is x equals 1. Now on this new scale, let's call this x prime. This same point is going to happen when x prime equals 1 times 1/2. So now point 1/2 is this flat point. So it looks something like this. Maybe. So we've zoomed out in this case. Sorry. So we can say that if b is, does everybody understand what's going on? Or is this unclear? So what I'm doing here is I'm rescaling my x coordinate, and that's going to do the same thing as zooming out or zooming in. So why don't we just test this out? Everybody has a computer, or most people have a computer. Most people have Mac. So pull up that graphing program, Grapher. And if you guys don't have a computer, you can work with somebody next to you. Or if you don't have a graphing program, you can work with somebody next to you. So just open up a linear plot right now. Okay, so now I want you to plot a parabola. Let's plot y equals x squared. Do people know how to use this? Okay, so you just choose default. You want to choose linear and you want to choose default, and you should just get a blank sort of coordinate system. So classic, choose classic. I think that. Actually, choose default. Yeah, so you want to do 2D graph and you want to choose default, and then you want to plug in y equals x squared and plot that. You should get a problem. Now what I want you to do is I want you to do this. So I want you to, instead of plotting y equals x squared, so we had before y equals x squared, now we're going to change the variables. So now I want to go to y equals bx squared. So this is what we're going to change it to. So we're in parentheses, we're going to multiply the x by b. And let's make b equal 1/2. See what happens. So make sure that the b is inside of the parentheses. It's getting squared as well. That's really important.
Oh, it's like b.
Can you put a B in there?
So just put a number. Put it in 1/2. You can't put in variables. So what happened when you put it in 1/2? What happened to the? Did you zoom in or did you zoom out on the x-axis?
You zoomed in.
You zoomed in, right?
No.
So what we're going to do is we're rescaling. This is the rescale. Or we can think about this as zoom. And if b is less than 1, we're going to zoom in. If b is bigger than 1, we're going to zoom out. So this is sort of a mathematical way to zoom. Okay? And we can do this for either coordinate. We could do the same thing for y. We could multiply that on the left side by some number smaller than 1, and it would be like zooming in to the y-axis. And we can multiply it by some number bigger than 1, it would be like zooming out. So now what we want to do is we're going to figure out what does this do when you do the same thing on a log-log plot. So now I'm going to plot, instead of y equals f of x, I'm going to plot log of y equals some function of log of x. So let me write out these steps. Log of f of e to the log of x times b. So that's what happens if I take a log on both sides. And this whole log, e to the log business is just a tricky way to get back xb. So if you look at this function, and you look at this function, you'll notice all I've done is take a log on both sides. So let me give you guys a second to catch up. And you don't worry about the log part right now. So what is everybody still doing the parabola? Is everybody done with that? Yeah? Okay, so don't worry about this log thing yet, just look up here. This, I can rewrite this as log of y equals some function g, which is this log f e thing, of log of x b. And using this rule up here, I can write this as log of x plus log of b. So what happened, essentially, is when I just had f of x, I would just get log y equals, let me compare this to, so this is rescaled, and this is original. So originally we had log y equals g of log x. So recall that if you do this, if you take your x coordinate and you add some constant inside of the parentheses, that's like a shift left or right. So remember, like, again, this is going back to probably high school. If this is a parabola centered at 0, this will be a parabola centered at A. So we're doing exactly the same thing here. So this tells you that zooming in, so zoom in log space is like a shift. So if we zoom into the normal space, in linear space, it's like shifting the function in log space. And we can be a little bit more explicit. We can say that if we zoom in, so if we make, so if b is less than 1, then log b is going to be negative, because log of something less than 1 is a negative number. And we're going to have exactly a situation over there, so it's going to be a shift to the right. So zoom in linear space is like a shift to the right in log space. And zoom out is shift to the right or a shift up, depending on which coordinate we're looking at. So right or up, and a zoom out is like a shift to the left or down. Okay. So now we know what zooming, we know how to do zooming mathematically, so we can sort of investigate scale invariance. And we know how to translate that to the log-log plot. Yeah.
Sorry, I just don't quite understand the first two steps on the right side of the board. So the
Here?
first one, yeah, between those.
So all I've done here is I took a log of both sides,
Okay.
and then I rewrote x times b as e to the log xb. This is natural logarithm. So this thing is just like e to the log xb is equal to xb. The only reason I did that is because I want to write the function, I want to write it as log of y as a function of log of x. So I can see what it looks like on a log-log plot. So that was sort of a trick. And if you didn't follow that, again, don't worry too much about the details, it's not that important, I want to show you that it works, but you can trust me that zooming is like shifting. That's the important thing to get out of this. Okay, so what I want to do now is I want to go back to this picture here. And I want to think about what this means. So here's my original plot, and now I want to zoom in. So let's say I want to first zoom in on the x-axis. What do I do to this line? Shift it, yeah. Which direction?
Right.
Right, yeah. The answer's over there, right? So if I shift it right, that's like zooming in. Can I get some intuition for why that is? Yes. So this thing, imagine this is like 10, 100, 1000. Then before my values ranged from 10 to 1000, now they range from 100 to 10,000. So I have zoomed in. Some of this is a little bit confusing. You might be going a little bit too fast. So you might want to, at home or something, think about, is right shift really zooming in or is it zooming out? But that's right. So just believe that for now. Now, if I want to, now what I can do is I can now zoom out on the y-axis. And zooming out on the y-axis is like shifting down. So I can shift it back down, and because it's a line, I can get the same picture. So I start with this, I shift it over and I get this. I shift it back down, and I get this again. So what I've just done is I've zoomed in on one axis, I've zoomed in or out on the other axis, and I've got the same picture back. Why is that important? Well, that's really what scale invariance means. So when we think about scale invariance, we think about, I'm going to write down a sort of intuitive definition of scale invariance. Or an operational definition of what you might actually do. So the first thing you do is you zoom by some factor in the x direction, and then you zoom by some other factor, in y, and if it's scale invariant, you get same picture back. So I want to convince you guys that this is really what scale invariance means. So let's look at the graphing program again. And what I want you guys to try to do with a partner is zoom in, so use your parabola again, zoom in by some factor on the x-axis, and then figure out what factor you have to zoom in or out by on the y-axis to get back to the same picture. Is that clear what we want to do? So let me say it again. You plot y equals x squared. You can zoom in to the x-axis, and the way you do that on this plot is you go to window, you go to window real quick, window, and then you go to, no, it's actually view, and then you go to frame limits. So that way you can adjust your axes. So for example, you plot y equals x squared from 0 to 10, then you plot it again from 0 to 2, that's like zooming in by a factor of 5, and then you figure out what you have to do to the y-axis to get back to the original picture you had. The numbers on the y and the x-axis are going to be different, but the function should look this way. And if you can do that, that means the function is scale invariant.
So minus 1 to 5.
Huh?
10 times.
Wait, why did they do that?
So that's the same as y.
Yeah, if you want to-
So we're gonna have to remember what that looks like. And
But
then
if,
try
so
to
if you readjust the axis, that's right. Okay, now we're
readjust the axis.
yeah, so like where
let's do
you're plotting it from
Oh, no, we can.
-5 to 5, and then so plot it again, but do it from -1 to 1.
Yeah, but
This is not scale invariant.
so
yeah.
it zooms in.
Or then like
I'm just 0 to
Oh,
5.
adjust back.
Click on the
Make it
plus
look like that.
sign at the bottom, plus button, and the new equation.
Oh, wait, this is a scale thing here.
This
Onto
is,
that,
that
okay.
equation is already equivalent to,
Right.
that's the same as y equals x squared,
What I'm
right?
supposed to do is try and
Oh.
get.
Like you wanna zoom in and then you
Yeah.
wanna see what you have to do to the function to make it so that it looks the same.
Okay.
I don't think so.
Oh no, I think that's just the two cases. So we're saying if you zoom in by
Oh, it worked.
2,
Start with pressing like select it and then start pressing them.
How will we test that?
So start
Weird.
with just
I don't know
put
what's
the
in
graph of y and
Change
Yeah, just a minute.
then change the axis so that it's from negative 5.
Oh, didn't do it. That.
Okay.
Okay. So
Okay.
this is
Oh.
what we wanna get
So
back
like
to
using
eventually.
Think of that.
If this curve
So-
Now,
So it works
go
with,
and
say,
change
the
the axis
1,
to
1
negative-
point.
from
In
negative
case
1.
anybody's having trouble, this to give you an idea of what's going on. You start with the picture looks like this. You zoom in to the x-axis. Now it looks doesn't look the same anymore. And then you zoom out on the y-axis until it looks the same again. I'm going to figure out what factor, if you say zoom out by a factor of 2, what factor do you have to zoom in by this axis?
And instead of doing something to the function, see if you can change the
It'll
so you
look
can
the
zoom in
same.
and
That's
if you go back to
and
like
that's
the-
what it means by scale.
instead of zooming in and zooming out, there should be an option that can like rescale your axis.
This is the original one.
Okay, now let's take this and shrink it.
So set x from -1 to 1.
Oh, okay. Okay, wait, so I haven't actually.
Okay,
And you wanna play around with y to
This
try
should
to
be
get it back to
from this,
that
But,
initial.
okay, so if we're gonna increase this
Okay, so I'm gonna do it by
So you kind of like do
Yeah,
this and track
this
and
has
stuff,
the
how I need to make y a little
5
longer.
minus, sorry, this one is -5.5, this one is -0.5 as well.
What's the
And
And I multiplied that by 10.
Which is
No.
Still the same.
So how
Back
much?
to
Doesn't matter what this is not quite the same.
Square.
Say if you double
Is it the same?
bring it to half.
Is that what you want?
So you can start by,
Well,
you can
so the
start by going back.
It works for the line.
Set the axis to.
so this says,
And then same for y.
so it says that the scale invariant just by
What's not?
This is where we want to get back to. So.
It will be the same transformation.
Oh,
It's not scale invariant though.
because y is a
So
different
this is the
scale
other
than x.
5 and 5x squared.
Right.
Now, if you divide,
So one way to do the question is, because I think it rescaled the axis.
no.
It's just that in one case we scale that
Oh,
axis,
wait.
while in the other we change the number, so this could be, we would have to change the limits to the
So then there's the question,
So let's try and make it.
so basically
Thinking this one?
So that's close, but initially.
the axes are the
Oh,
identical.
wait.
Is about
This is supposed to be linear.
That's what I thought.
Right.
These are supposed to be linear.
There we go.
Yeah.
That's what I meant
So
to
we're
do.
trying to figure this is not the
So-
ones that we saw that.
Well, it
Basically,
should be
So,
possible, it's just
What
that.
I'm thinking is if this was divided by
you
one,
can decrease it down to
you would
10%.
get
The
a
X structures and your 10%
squared,
which is
If
good.
this was divided by 1.
Yeah, exactly. Because now they look the
So-
same.
axes.
But if I look at the numbers, they're different.
I think the point is to get the
But
same
this is
shape.
not a skill for
And it will get this regardless, if you just
Right,
divide this
quadratic
whole
is
thing,
That's a question, that's a good question.
then the axes will.
Should it be impossible?
Oh,
Is it expert
so
Carlo?
you're talking about the actual axis, in order to see that it different zoom level, I think that.
See, you've been dealing with parabolas all your life, and they've always been parallels.
Okay.
Yes, they are scale invariant.
What
Okay,
I'm
so,
saying is anything which is x squared.
Did most of the people get done? Did it work out?
But.
Okay, so what did we have, so if you zoomed in by a factor of,
Okay.
2, what did you have to zoom out by on the y-axis to get to the same picture? Yes, if I zoom in by a factor of 2, so let's say that this is a factor of 2, so now I'm looking at 0 to 5.
1.4. I'm just guessing. Square root of 2.
Okay, so the way we can do this mathematically is we can say y equals, what, we're going to plug in a b here, bx squared. And what value does b have to be if we want to zoom in by a factor of 2? Is it a half or is it 2? Let me just check. I want to do it wrong. Yeah, if we want to zoom in, it's a half. So this thing is going down to be a quarter x squared. And so if I bring the 4 over to the other side, I get 4y equals x squared. So the thing I'm going to be doing is I'm going to be multiplying y by 4, which is the same thing as zooming, as doing what? Zooming in or zooming out? Zooming out by a factor of 4. So if I zoom in by a factor of 2, I have to zoom out by a factor of 4. If I zoom in by, let's try this again. If I zoom in by a factor of 3, I have to zoom out by what? 9. Okay, so we've all figured out the game. This x squared tells you how you do it, right? So I want you to try it again now for, okay, so then here's the question. Look at that definition of scale invariance. Is this scale invariant, this function? Who says yes? Raise your hand.
Wait, sorry, x squared.
Is y equals x squared, is that scale invariant? Who says yes? Who says no? Okay, so remember, if it's scale invariant, it means these things are true. So we zoomed in by some factor in the x direction. We did that. We were able to zoom out by some other factor, and we got the same picture back.
And the same
Other
axes, or just the same
Any other factor.
look?
Different. We can't, if it's the same axes, you wouldn't have done anything, right?
This is some other factor.
Okay, the same ratio of the axes,
Yeah, some other factor to be determined.
So yeah.
but will the axes be in the same ratio? Because we discovered that we could just multiply it out, and we get the same looking curve by stretching the axis to match that.
Exactly.
That's scale invariant.
Yes.
Okay.
So that's one way of understanding scale invariance. I think it's the most visual way to do it. So y equals x squared is scale invariant. Could we have guessed that? Well, yeah. It follows this, right? The alpha would be -2 here. It's a power law, so it better be scale invariant. Let's try something that's not a power law. Let's try to play the same game. Be a little bit more frustrating this time. So let's try
I
x.
want to say something really quick.
Yeah.
The other factor that you have to scale out on the y-axis, it's actually really easy to find, right? Because you have x to the alpha, and you can immediately like take things out and find the factor on the y-axis.
Exactly.
It's
So let's
one
say
factor, and you can find it easily.
if this weren't squared, but it were just some alpha here, then you'd always get b to the alpha, x to the alpha, and so your other factor is 1 over b to the alpha. So for any power law and for any scaling factor, I can tell you what I have to rescale on the other axis by to get the same picture back. Let's try again with an exponential. So now what you want to do is you want your function to do this, and you want to try to do the same, play the same game.
You start off like
This is
shot.
I think it's
You
applying
Oh, yeah.
still the same person.
Okay, well, I don't know, my feeling is that we're not gonna be able to do it. Actually, going from the.
from the fact that
Which explanation? Like,
the fact that it's not mathematically possible.
yeah, so something
Okay.
something to the x. Something.
Let's see,
Huh?
let's try, why don't we
Maybe X?
try and do
It could be
the weighting of like
X or
the same
minus
thing
X.
as we did with x squared, but let's try to do it.
So that's a curve.
So, before we
If you do -1, and you can get y equals whether it's -1, then it'll go through 0. So you can try to solve it. It'll be easier to tell the x is a.
what would we have to do?
Okay.
By whatever way.
So change the full limits back to starting from if I use 10 to 10 to 10 as my.
Oh, versus like,
So if you type -1.
versus like,
So this is saying that if you change your x scale
versus like,
I was just saying.
this is not
So
scalar.
expand x basically, so I'm saying 10 to x to the half.
and then you have to change
Versus
y
this is
by a
not
factor
scale
of
variant.
4.
in the opposite direction.
No, it's still like,
Yeah.
what's something that's mapped?
So that's
Oh,
my,
oh.
my theory is that you have to.
It's not?
Okay, that was.
Let's try out. You can multiply by
Let's
e
do
to
it
the
within the
power
form.
whatever you
Yeah, it is.
right?
So let's change get the same one here.
But you're not multiplying it, is my theory. When you're stretching the axis, you're multiplying, I think, the whole right side.
Yeah.
Oh, let's do the same thing, multiplying
So the really just
1 over the multiplier times
scales
x.
in the equation, it was just changing
So multiply that frame
Okay.
by 10, then you're
So now
taking
we're
away
going to
size.
do this one something negative.
Oh, you're right.
So in that
You're
case,
totally right.
Oh,
Try this.
multiply it by something.
Yeah, by some.
So only thing I can do is multiply it by a factor.
What if?
That or
Right.
multiply
I
the
can't
x
multiply
by
the
a
x.
factor.
Well, we have to do
No, I
1
think
over.
I'm not allowed to
right?
do that.
Isn't that the
I
thing you
guess
want
you
to
could.
scale?
if we multiply
Either
if
way,
we
right.
times
look at
10,
that one, but
then you get
You can try.
negative 1/10 x.
Wait, no,
Can't
what's
see
the negative?
Yeah, I think it's change negative one.
Okay, so everybody,
Frames.
I know no one's done. Has anybody been able to successfully get them to look the same?
Yeah.
Yes? No? No. So why not? What happened? What was different about this time? So when we try to rescale again, what we're doing is this thing is going to e to the minus x times b. That's zooming in or zooming out of the x-axis. And I like to separate it like I did before. Now this thing, the problem though is this thing is e to the minus x to the bth power. And if I want to get back to the same function, I would have to take the bth root of y, and that would give me e to the minus x. But the bth root is not scaling. I'm not multiplying it by some number. I'm doing something else. So this isn't allowed. So the conclusion is you can't do this. You can try and you can try, but you'll never succeed. They can't look the same. And the fact is most functions are like that. What I want to convince you of by the end of this class is the only functions that you can play this game with and do it successfully are functions like this, power laws. Okay, so does everybody at least fail? Because if you failed, that's good. If you succeeded, that's bad. That means you failed.
So everybody sounds.
Okay, so now the last thing we need to do is we figured out that certainly exponentials are not scale invariant. And we could have guessed that because we know that they have a characteristic scale. Typically we write this thing as like minus x over lambda, where lambda is the decay constant. And that would be the scale in this case. So it's not scale invariant, it's heavily dependent on where you are with respect to the decay constant. So what we want to sort of prove now, and Newman does this in a mathematical way, is to show that power laws are the only scale invariant functions. He does this on page 11, and he does it by taking some derivatives and some stuff, and it's not so easy to follow. At least you don't get an intuition for what's going on here. So I'm going to do it in a different way. So in order for something to be scale invariant, we learned that we have to be able to zoom in by some factor on the x-axis, zoom out or in by some factor on the y-axis to get the same picture back. Let's investigate what that would mean on log-log space. So in log-log space, if you have some function, that means you have to be able to move the function over by some amount. That's like zooming in. Pretend like that looks the same. And then you have to be able to move it back down by some amount and get the same picture back. So one way to think about this is, we know for a line this works. We know that we can move it over and then move it back down and get back to the same point. So this thing right here that I'm drawing, this is like zooming in and then zooming out on the other axis. Think about this as like the zoom path, sort of the path you take in zoom space. And all these concepts are crazy. But if this point looks the same as this point, that means that you can do this. Because this point will get mapped to this point after I zoom in, and it better look exactly the same. Otherwise, it's not going to be scale invariant. Otherwise, the picture won't look the same at the beginning. So certainly for the line that works. What about something like this? So if that was what our function looked like in log space, we would move it over and move it down, and we'd get something that looks like this. Well, that's very different, right? So a way we can think about that, actually a better way, is we just draw this picture, and we say, is there any sort of path we can take from one point to the other, and we get back to the same looking point? And here it doesn't look the same. Here the slope's something large, here the slope's something smaller. The whole picture looks different. So one way to think about scale invariance is if you plot it in log space, if you have to be able to move over by any amount. That's like zooming in by any amount you want. And then you have to be able to move back down by some amount and always get back to the same point. So you can do this for any, this is like B, and these are our 2 points. And so the 2 points should look the same for any B. That's the same thing as saying the picture will look the same if you zoom in by any factor, and then rescale the other factor appropriately. So, if we want to prove that power laws are the only scale invariant functions, we have to prove that we can only play this game for a straight line, not for anything else. So some of you that might be obvious at this point, some people want to be confused, so I want you guys to again get into the same groups and sort of try to convince each other why a straight line is the only one you can do this for. And things like this don't work. Okay, so are people unclear? Unclear what I want? Is my question clear? Is what I'm doing here clear? Okay.
They must have the same.
But a stair step and you move a block down by one step.
You don't have to, you are.
But that's a good example because they are.
I think the writing down.
That's obviously set. And all relates to what we were
But it's what you said, you can do half a step of each.
But if it's a problem, then every step is
Zoom by any factor. They're zooming for any x there is some.
Yeah, that have only with also only subset.
Look at like shapes of
So if you move x anything,
So what about Mendelbrot?
then you move over and then you go down.
Could have anything.
Oh, is that what he's saying?
Repeating a step.
Oh, that makes way more sense, actually. Sure,
I guess the way of it would be to show that it is symmetric and the same.
So yeah, the curve is like flies way out and
So the only makes the target fast symmetric.
And then you shift over to you multiply that by the same factor.
Yes, we get
2, so 2,
I was really sure.
8, 16, 32.
So, for example, when they zoom in, this looks like
So let's see if these two steps correspond to a factor multiplication by here. So as it's log of 2, let's say that all of this is just log 2.
unless it's true, it's not.
And then each step corresponds to 1 unit change, and each unit change corresponds to
Says that in this thing,
And so, you say like, yeah,
f
I don't know like which one is what, because it's like 300.
the curve is y, right?
And actually,
That's all it is, because like a zoom out, it looks like
Shifting one factor says
So group here.
What's that?
So quiet. A group here is so quiet.
Oh,
You have an exercise, Mark?
No, but actually
I'm done.
Okay. So what is the conclusion? Yeah.
I just had this idea, and it's probably wrong, which is that if you had a fractal shape,
This exists.
A fractal shape
a fractal curve
in the log space.
in the log, or in the
Same apple.
In the linear space.
in the log space, yeah, sure.
Okay.
Then looking at it at a certain zoom level, it'll look one way, and if you zoom in, if it's fractal to like a really high degree, it'll look exactly the same.
Yes.
So it turns out zooming in log space is like exponentiating in linear space. So I was thinking about this yesterday actually, and what does that mean? I didn't think about any sort of implications that are important, but maybe there are. It's interesting, isn't it? Think about zooming in zoom space.
But I'm just saying there could be a curve that appearance-wise looks the same as you zoom in.
Remember, in this space, we don't
That's
want
only
to
for
zoom, we want
certain
to
zooms.
shift
Oh, right, yeah.
in order to zoom in the other. So I want to look at this picture because certainly I can play this game here. I can zoom.
So what's a fractal?
If I zoom by this factor and go like this, it looks different. But if I always do it by a multiple of this spacing here,
It's not scaling.
I can always get back to the same point. So is that thing at the top scale invariant? Some people say no. So why not? Yeah.
I mean, I can't like explain this in a scientific way, but like if you zoom in on the corner of the stair,
Mm-hmm.
like up there versus the like concave corner, it's gonna look different.
Yeah. So when you say zoom, do you mean move over by a step like this?
Yes.
Okay. Yeah. So yeah. So like if I start here and I move over, I could think about scaling. I could think about zooming so that I'm to this point and then moving down. And I'm going to be here, and that's clearly a different point. So what is this?
Clearly different point?
Huh?
What do you mean? It still looks like stairs.
Same curve though.
Yeah, but here the this is
This is
clearly a
regular
different point
stairs.
than this. Huh?
Like, just saying it still looks like stairs, right?
But the exact point is a little, looks.
The neighborhood of the point has different characters, like there's different slopes. This point right to the left of it is infinite slope. This point right to the left of it is a zero slope. So these 2 points are different.
So what
Right?
is
So this point looks characteristically different than any of these
Interesting.
So that's,
blue points.
the inner corners and the outer corners.
Yeah.
Yeah.
Yeah. The inner corners and outer corners are different. So what this tells you is that if you zoom by a particular factor or a multiple of this particular factor, which is the size of this step, you'll get back to the same picture. If you try to do some zooming in between those two levels, you won't get the same picture. So this is fractal-like. It's not scale invariant, but it would be like a fractal where you zoom in, and as you zoom in slowly, things look different, and you zoom in a little bit more, and now things look the same again. And then you zoom in a little bit farther, and things look different. You zoom in, and things look the same as they did originally again. Yeah.
So I think so. This, if you there are multiple possibilities where you can zoom in and perform and find a zoom out so that you get to the same shape here. But and that's fine. Like even if it's not the same point, the curve basically looks exactly the same. But I think what's important about the scale invariance definition is that it's for any factor. So here you can definitely find a zoom in factor where you can't find any other factor to get back to this shape. So even if you can find some factors, you get back the same curve, but you can definitely find factors where, and that's important. For the line, no matter how much you zoom out or zoom in, you can always find the equivalent to zoom out to get, like for any factor. And that's a big, important issue.
So the first one is for all x.
And the second is
It's not
there
X, it's
exists.
for all
Exists a
For all
lot.
zoom factors.
For all
Right.
factors.
Okay, so
then
for
there
all
exists-
factors, there exists another factor.
Yes.
And in the fractal-like, it's a discrete set of x's maybe.
Instead of B's, but yeah.
I mean, I'm
Factors,
sorry, I
yeah.
keep looking at the x's.
Yeah,
not the
exactly.
b's.
That's exactly right. So, just like you said, Oana, I have to be able to, I can say I'm going to move to the left or to the right by 1, and you have to be able to tell me what I have to move down by to get back to the same point. If I tell you I'm going to move to the right by this distance, you can do it. But if I tell you I'm going to move by this distance plus a little bit more, there's no amount down I can move to get back to the same looking point. And so there's only particular zooms that you can do. So this would be like if you had the function, you zoom in by a factor of 2, you can't do anything to the y-axis to get back to the same picture, but you zoom in by a factor of, let's say, 4, and then there's something you can do to the y-axis to get back to the same picture. So, we showed, last time we looked at that fractal, I think it was the Mandelbrot set, and we were looking at it zooming in. This is exactly the same sort of character. So remember we zoomed in a little bit and things looked quite different, and then finally we zoomed in enough and we got back to that little circle again, and things looked exactly the same. And then we zoomed in a little bit more and things were different again, and then we got back to that same circle. So always return back to the same point. Yeah.
But then if you take that fractal-like curve and you really fractalize it,
What do you mean by that?
instead of taking every straight line and breaking it up into a sub-stair step, etc. So you make that line, which is stair step, into a true fractal line.
Well, remember, the thing that we want to be fractal isn't this plot, but it's the plot in
I'm
linear
going to
space.
try. I mean, it looks like it's the first stage 1 of turning it into a.
So now you're saying
fractal.
make each of these steps half the size?
Right.
And then make them half the size again?
Right. So now you've turned it into a true fractal curve.
The limit of that though is a line.
Well, the limit in some sense is a line, but it's also a fractal. Is a
It's not a
downgoing
fractal.
line.
It's not a fractal.
It's not
Because
a fractal.
if I zoom out really far, it looks like a line because I can just blur together all the little steps. If I zoom in really far, it'll look like a staircase again.
No, because it's an infinite fractal. It won't look like a staircase. It'll still look like.
You're saying this, right? Little steps like this.
Now fractalize those.
What do you mean by
I mean,
fractalize?
Take every one of the steps and divide it in. A fractal goes all the way.
Then you'll get smaller
Then it'll be a line.
steps.
You can do it all the way.
Then you'll get smaller
Right, if
steps.
it goes all the way, it'll look like a line no matter how far you go down, but it's still never gonna, it's every point.
If you
is
go all the
a
way,
tangent.
it's a line.
saying? It approaches
Okay.
the line.
This isn't a fractal.
It's not a fractal. Okay, never mind.
Because the steps are, there's only one step size, right? You're saying just make the steps smaller and smaller and smaller and always have one step size. Or are you saying
Okay.
have many different step sizes?
Okay, never mind.
Okay.
With you many
It's a
different
fractal.
sizes, you're not gonna have the fractal like. You're not gonna have a true fractal.
So the only
You're not gonna have a scale independent.
right. So the only scale invariant function that we can draw in log space is truly scale invariant. Is a line. Now what that means is the only function that we can write down that's truly scale invariant is a power law. So just to remind you how we get from that, we can say, well, we have a log plot, log y equals mx plus b, because we know it's a line. I did this at the very beginning, I'm gonna do it again, we exponentiate both sides, and we get that y goes like x to the n power. So this form of a function is the only scale invariant function that there is. That's really important, because that means that if you have a system that's fractal-like in any way, meaning it's scale invariant, it's going to have some aspects of it that you can describe as a power law, because that's the only function that sort of matches up to that scale invariant behavior. So that's why people get so excited about power laws. There's these strange things about them to be careful about, the fact that there's no well-defined mean, and variance and things like that, and the fact that there's no typical scale. But when you see one in a real system, when you sort of discover one, the important part is it tells you that something about your system is fractal-like, and something about your system is scale invariant. And the hard part is figuring out what that is. And again, that's why it's important to distinguish between a true power law function and a log normal distribution, let's say, because one of them is truly scale invariant and one of them is not. And so there can be a big difference in systems that are truly scale invariant and systems that are only scale invariant over some range. And you want to be able to distinguish between those two. So we didn't get a chance to talk about any of the sort of ways you can get power law distributions. And the last part of this paper was about combinations of exponentials, and there was something on random walks I didn't have you guys read. The more important ones were the Yule process and the phase transitions. And I'm not going to go into those, but I just want to say something about this whole percolation thing. So just recall what was going on here is you want to color some fraction of this square black with little black dots. And then you ask the question, on average, how many black dots are connected together? And it turns out that you get some sort of scale invariance for this type of system. And I want to say that this type of system is a fractal. So if I zoom in by any scale, I'm going to see sort of on average the same number of dots, because everywhere in this box has the same density of dots. So I guess the point I'm trying to make is it shouldn't surprise us that we get a power law in that case. And it shouldn't surprise us that we get a power law in all these other cases that we talked about, like income and well, what are some other examples? So we talked about income, we talked about word distribution, word frequency distribution, we talked about, what were some other examples of power laws that you mentioned at the beginning?
I mean, from paper.
Yeah, in the paper.
Size of cities.
Size of cities.
Number of, the length of words. I think.
Length of words. All of these things have the property that there's not a good characteristic scale. Cities don't have a good characteristic scale. There's no average city size, really. Intensity of wars, yeah, there's small wars, big wars. You can tell all these things are scale invariant. Another important property of a lot of these systems is that they're hierarchical. They're built, that sort of the big pieces are built from combinations of the small pieces. In some sense, you can think about the economy working that way, although it's not so clear. And anytime you get a system like that, so this Yule distribution, this Yule process was an example like that, where the big groups of species would produce a small group of species that would grow, and that would produce a smaller one. So just like fractals are sort of built up in this hierarchical way, and therefore don't have a scale. Things that obey power laws, I'm not going to say always, but often you can think about them in a hierarchical way. And you can always think about them as having some scale invariant properties in big fractal. So those are the important parts. Hopefully this was useful, or maybe it was just confusing, I don't know, but Zoom speed. Anyway, I'll see you guys next week.